Hello everyone. In the previous videos, we have seen the applications of TOC. We have also looked at the basic mathematical foundations which are required for learning TOC. And then we have also looked at the notion of alphabets, strings, languages, and grammars. So in this video, we are going to shift our attention towards finite automata, or it is also called finite state machine. So we will look at the different categorization of finite automata. So there are few categories of finite automata. So we will look at the categories of finite automata, categories of FA. So remember that finite automata, in short, we call it as FA, and it is also called FSM, which is actually finite state machine. So in short, we call it as FSM. So in this video, we are going to look at the categories of FAs or FSMs. And then before giving the mathematical definition of what is an FA or an FSM, we will look at some few uh, examples of FAs based on the given applications. So it is always learning through examples is always the best way to learn something. So once we are familiar with the construction of FAs, then when we look at the mathematical foundation, the mathematical definition of how to create an FA, it will become more clear to you. So basically, what we will do is we will look at few examples of constructing constructing an FA, constructing an FA, finite automata. So when we look at the categorization of FAs or FSMs, there are broadly two categories. One is that FAs with output, or one is without output, and the other one is with output. And in the category which is without output, we have two varieties. One is called a DFA, and the other one is called an NFA. A DFA actually stands for deterministic finite automata. So the letter D stands for deterministic. And similarly, NFA stands for non-deterministic finite automata. Also to be noted that for NFA, you have one more type called the epsilon NFAs. And this is with regard to the FAs without output. And again, there is a category called with output, and in that we have two different kinds of machines. One is called a Moore machine. And the other one is called a Mealy machine. Okay, so we are actually going to focus our attention in this video. We are actually looking at the category of FA which is having no output. So we are actually going to look at this particular category in this video. So again, we will be looking at very simple and elegant examples only. In the course of time, we will also look at few complicated examples. So once we are familiar with some examples, then it will be easier for us to understand mathematical mathematical definition of what is a DFA, what is an NFA, etc. So we will initially we will look at a few examples of few very simple and elegant examples of FAs. Let us look at the construction of some very simple finite automatas. In this example, we are going to construct a DFA to accept all the decimal numbers starting with 9. Okay, so to construct a DFA, there are two ways of constructing a DFA. One is to have the transition diagram. One is through transition diagrams, and the other method is by using a transition table. By using a transition table. Again, in this video, we are going to look at the construction of FAs using transition diagrams. A transition table is also a very elegant way of representing an FA. So we will look at that method also in our future videos. So, but in this video, we will be focusing on the creation of FAs using transition diagram. So let's look at the example which is given here. So we are asked to construct a DFA to accept all decimal numbers starting with 9. You may be already aware that a decimal number consists of numbers from 0 to 9. So the alphabet set of a decimal number system starts from 0, 1, 2, and it goes up to 9. So these are the valid alphabets in this language. And to construct a DFA, we make use of some states. So there will be a starting state and there will be an ending state. So to start with, let's draw a starting state. So let me say Q0 is my starting state. So a starting state is always indicated by an arrow from the left side. So if you see this kind of an arrow, then it means Q0 is a starting state. Similarly, an ending state is actually represented by a double circle. So if you see a double circle, then it means that that is the final state of this FA. So remember that there can be multiple final states for a given problem, and in some cases there are not even a single final state. We will look at few examples without final states, and we'll also look at some examples having multiple final states in the course of the study. So, the current problem is to construct a DFA which accepts all the decimal numbers starting with 9. So uh, it means that if you are getting the number 9, so to start with, you are in this state. So you are in Q0. So you are in Q0. Okay, so you are in the starting state, and you will move to Q1, which is the final state, only upon getting the symbol, getting the alphabet 9. So if you get a 9, then you will move to Q1. Okay, so that's the start symbol, and then and once you get a 9, you are not actually bothered about the rest of the symbols. So you can say you stay here. You have to stay at Q1 if you are getting 0, 1, 2, 3, 4, 5, 6, 7, or 8. So if you're getting even 9 also, you can stay here upon after the first symbol is 9. You can have any number of symbols, and which can range from 0 to 9. And also remember that in the first instance, if you are getting a symbol from 0 to 8, then you should not accept it. So that there should be a dead state going from Q0, say, to let's say Q2, or let's indicate this as QD to understand it as a dead state. This is a dead state. So if you are getting the initial input as, if you are getting the initial input as 0, 1, 2, 3, 4, 5, 6, 7, or 8, then your machine you will you will make your transition to a dead state called QD, and hence you will never reach to the final state. So in this DFA, it indicates that if you get a 9 as the initial symbol, then you can go to the final state, and after that uh, you are really not bothered about what kind of symbol, that what kind of alphabet that you're getting. For example, in this case, let's take the number. Let's take let's let's assume that our string that we got is 8462. So what will happen here? Again, don't forget to draw all the transitions. So from QD, if you are getting anything, you stay here in QD itself. So you are not actually bothered. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So from QD, if you are getting 0, 1, 2, 3, 4, whatever the symbol or the alphabet that you are getting, you are going to stay there itself, because your starting symbol was not 9. So let's go through this. Let's go through this example. So it will become more clear to you when we are working on this example. So the first symbol here is 8. So I have already told we are in the starting state. Initially, we are in the starting state. So when we see an 8, the transition 8 is here. So we'll be moving here. And the next symbol that we see is 4. So from here, 4, the transition of 4 is already defined here. So we will stay here. So we have encountered this symbol, 8 and 4 symbols are already encountered. And the next symbol that we see here is 6. So 6 is also defined here. So we will stay in QD itself. And then we'll see the symbol 2, or the alphabet 2. Alphabet 2, the transition of alphabet 2 is also defined to the same state. So if you are getting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, anything from here, you will stay in the same state. So that's why you're going to stay here. So if you're not getting, if your first input is not a 9, then you will be always in that state, and you will never reach the final state. Now let's look at another example which is valid for this, which will be accepted by this DFA. Let's look at, say, the our example is 9, 1, 4, 6, 8, 7. This is the number. This is the string that we want to check. So if this string is given to this DFA, since the first input here is 9, if you are getting a 9, the transition is from Q0 to Q1. So you will be going here. So you are already at the final state. Now, if you are getting a 1, the transition of 1 is defined to be staying in the same state. Similarly, the next symbol is 4. The next symbol is also defined here, and so it will stay here itself. 6 is also defined here. The next symbol is here is 6, so 6 is also defined, so you'll stay here. And 8 is also defined. 8 is also defined to be staying here. Similarly, 7 is also the transition of 7 is also to the same state. So essentially, what happens is that if you are getting a 9 in the 9 as the initial alphabet of the string, then you are already in the final state, which is Q1. And then any symbol that you're getting, you're going to stay here in Q1. But in the initial, if the initial alphabet is not a 9, then you will be shifting, you will be going to QD, which is at that state, and then you will be staying in that state, uh, that state upon getting any inputs, that is 0 to 9. So you'll be staying here. You'll never reach the final state. So this is the example of how we can construct a DFA to accept all the decimal numbers starting with 9. So here are a few things to be noted. Uh, you know, Q0 is our initial state. which is indicated by an arrow from the left side. Then Q1 is the final state, which is indicated by double circles. Similarly, QD is a dead state here. So we actually wanted to redirect from Q0 to QD upon getting the first character as 0, 1, 2, 3, 4, 5, 6, 7, 8. So QD in this case is a dead state. So, but in some of the DFAs, you don't need a dead state. Okay, so we'll encounter such examples later. And also remember that the final state, we have only one final state here in this example, but in some cases you can have more number of you can have multiple final states. But remember that you will always have only one starting state. You will never have multiple starting states. In any DFA, you will have only one starting state, but you can have multiple final states, or you can have no final states at all for a DFA. That's also possible. This is the example. This is the first example which we are going through. I think it's clear to you. Okay, so we'll see the next example. Now let us look at one more example. In this example, we are asked to design an FSM. We are asked to design an FSM to determine whether the given decimal number is even or odd. So remember, an FSM is called finite state machine, and DFA is one category of finite state machine. So it is actually asked to design an FSM, so you can actually design a DFA. So now our question is with regard to determining whether the given decimal number is even or odd. So we are already aware that if a number ends with 0, 2, 4, 6, or 8, then that number will be surely an even number. So it also means that if the number ends with the other numbers that are 1, 3, 5, 7, and 9, then these numbers will be odd numbers. So this will be the logic that we are going to apply in the construction of this DFA. So let's start. Let's get started. So let's say our starting state is Q0. So what is the minimum input that you can have in this case? So it can be a string with only length 1. So remember, very important that we always consider 0 as an even number. In computer science, in most cases, we always consider 0 as an even number. So this we have already encountered when we studied digital system design, where we talked about parity. Then we said that 0, if you get 0, 0 is considered to be an even number. Okay, so in many computer science related topics, when it comes to even or odd, you know, 0 is considered to be even in computer science as well as in mathematics. So it's very important to remember that 0 is an even number. Now, let's say the minimum string that you can get is with one character. It can be 0, 2, 4, 6, or 8. So if you get any of this, you will have to go to the final state, and then so let's draw it. Let's draw it. So from Q0, so suppose you are having Q1 as the final state, and it means that if you are getting a string of length 1, which is having only one of these alphabets 0, 2, 4, 6, or 8, you'll have to you'll have to make a transition to Q1. So let's say 0, 2, 4, 6, and 8. So if you're getting any of this, you will move to Q1. And from here, if you are getting again an even number, again if you are getting 0, 2, 4, 6, 8, you will be staying here. 0, 2, 4, 6, 8. Then you will be staying here. Now, what if we are getting the first character as a as 13579? Any single letter, a single alphabet string having 1357 or 9. It should not be accepted, right? Because it's not an even number. So we should actually draw a dead state here. Dead state here. I am drawing the dead state by indicating QD. You can also indicate it by Q3 or Q2 or whatever, it doesn't matter, but because it's a dead state, I am indicating it as a QD. Okay, so now if you're getting anything like 13579, 1357 or 9, then you are going to move to the dead state. But it's quite possible that after getting a 1, you may get a 0. For example, if the string that you're getting is say 10 or 12, this is an even number. So what we will do is that if you are getting an even number after getting the odd number, then we will make the transition from QD to Q1. So this means I will move from QD to Q1 if I am getting anything like 0 to anything out of 0 to 4, 6, and 8. Okay. Now, it's also possible that you keep on getting odd numbers after getting the first character as 1357 or 9. And if you keep on getting odd numbers, you just stay here. So it will be 1, 3, 5, 7, and 9. But what if we are getting uh, suppose we are getting 2, 1, 5, 6 as the string. This is an even number. This should be accepted. So we will have to make a provision to accept this. So what happens here? If you are getting a 2, you are in Q1. If you are getting a 1 and a 1, the transition is not defined. So we can actually define this transition to this dead state. Okay, you can go to this dead state. But if you are getting an even number followed by that, then you can always come back to the final state. That's what we are going to do here. So we are going to actually define that. We are saying that there can be a transition from Q1 to here if you are getting a even number. That means 1, 3, let me write it here, 1, 3, 5, 7, and 9. So if you're getting a 1, 3, 5, 5, 7, or 9, you can make a transition from Q1 to this dead state QD. And from QD, and from there, if you're getting an even number again, then actually you can make the transition. That transition is already drawn here. So if you're getting 0, 2, 4, 6, 8, then you're going back to your Q1. Okay, so this is how we can define the FSM to determine whether the decimal number is even or odd. We'll check with few examples. Right now. Suppose the given example is 2143. 2143. We know that this is an odd number. This is an odd number, and as per the definition of our automata, the odd numbers should not be accepted. The automata will accept only even numbers. So this number has to be rejected by our automata. Let's look at how this is happening. So we are initially at the starting stage. That is, we are going to be here initially in Q0, and from there we are getting a 2. So since the transition of 2 is defined here, so we will move here. So we'll be moving to Q1 like this. Okay, then from there we are getting a 1. So from transition of 1 from Q1 is defined to QD. So we'll be going here, and after that we are given with 4, so we'll be going back here because the transition of 4 is given here, and then again then we will encounter 3. We are encounter then we are and then we are having 3. So again we will make this move from here to here. So we will be finally at QD. Will be at the end of the string. We will be here at QD. So as per the automata's definition, the automata will accept only even numbers, and since this number is an odd number, this is not accepted by our automata. Now let us look at another example. Let's say our input is 2, 1, 3, 4. Now, as you can see here, the first input is 2 here. The first input is 2 here. So the transition, initially we are at Q0, and upon seeing 2, the automata will move to Q1. And at Q1, the next symbol at Q1 is 1. The next symbol at Q1 is 1. And so what happens is that it will go to QD because the shift of the symbol Q1 is defined here. So the transition will be from Q1 to QD. And after that when we are at QD, the symbol that we see is 3, or the alphabet that we see is 3. So what we'll do is we'll be staying here because 3 is defined as a self loop. So the transition will be again back to QD itself. So we'll be stuck at QD now, and after that we'll see a 4. So from here, when you see a 4, the transition is to Q1. So we'll be reaching at Q1, and that's the end of our string, and now we are at the final state. So we can say that this string 2134 is accepted. This string is accepted by our DFA. So the given DFA accepts all the even numbers and rejects the odd numbers. So that's what we are encountering here. Now an important question to be addressed here is that, can we draw this DFA in a different way? It's quite possible. What we can do here is that you can see here that there is let me take my arrows. Okay, so you can see that from Q1, if you're getting a 1, 3, 5, or 7, you are moving to the dead state actually. So you can, instead of doing that, you can also move to Q0. And from there, if you get a 0, 2, 4, 6, or 8, then again you can come back to Q1. So if you connect this this arrow, this transition path here, it is equivalent to connecting the same. You can actually delete this transition path and connect this transition path to Q0. That will also work in a very equivalent way. So let me do it. Let me erase that. And then and connect it to Q0. So it looks like this. You can actually erase this path. And then you can actually connect the arrow. From here to here. If you are getting a 1, 3, 5, 7, or a 9. And look at this. Whether this you can actually verify this DFA by putting up some examples. I think it's very clear that for the same problem we can draw a DFA in a different way. So the moral of the story is that for the same problem you can draw the DFA in different ways. So there can be multiple DFAs for a given problem, and that's why it's challenging to verify for a given problem. you can have multiple DFAs, so people can draw different DFAs for a given problem. So it's actually a little bit of a challenge to verify them and then verify whether it is correct or not. Now let us look at another example. This is going to be very interesting and also a real example, real time example. So we are looking at the design of an entry control system. Normally we see this in metro railway stations. So what happens is that we actually take a ticket to enter the platform. So what we do is that in the back of the ticket there will be a QR code. So that QR code will be shown to this machine, and once the machine identifies that this as a valid QR code, then what will happen is that these flaps will open up. These flaps will move and open up, and then the person who is having the valid ticket can get moving. So once he is moving in, there is an IR transmitter and a receiver uh, fitted to this machine. So the line of IR will be cut once he is getting inside the once he is moving inside. So after detecting his movement, the machine will automatically close these flaps again. So these are the actions performed by this machine. So we can actually define a DFA for this for designing this entry control system. So let's analyze what is happening here. Which are the which are all the states here, which are all the transitions here, and then we can actually design a DFA for this system. So if you look at closely, we can see that there are only two states. Let's define two states as Q0. The Q0 stands for closed, the state when the flaps are closed, and Q1 stands for the state when the flaps are open. So we can say that we can actually draw um, a transition diagram or DFA's transition diagram, say from Q0 representing Q0 and Q1. So remember, Q0 stands for closed state and Q1 stands for open state. So what happens is that here the alphabets of this language, you know, we can actually represent it represent it like this. If you show the QR, there are only two things that you are doing for transitions. You are going to show the QR code, and then you are going to move. These are the two actions that you are performing with this machine. So if you are at Q0 means you are at closed state, and then if you show a QR code, a valid QR code, the state will move. The transition will be from Q0 to Q1. That means the flaps will be getting open up. So the transition from Q0 to Q1, the Q0, we can assume that Q0 is the starting state. So when you actually show a QR code, the transition happens from Q0 to Q1, and after that, if you move, if you are moving in, then the IR rays will be cut, and then the flaps will automatically close. So what happens is that when you make a move inside, then from Q1, uh, which is an open state, when you move inside, it will shift to the Q0, which is a closed state. Okay. Now what happens if at Q1, if you are again if you are showing the QR, that means before even moving in, you are again showing the QR. You are continuously showing the QR to this machine. Means when you are at Q0, you are actually, the flaps are closed. When you show the QR, then you will reach Q1 because the flaps will get open. And again, continue to show QR. Then what happens is that the machine will open. The flaps will remain opened if you continue to show the QR. Um, Also, what happens at Q0 if you try to move in, if you try to make a move here without showing the QR, then the flaps will not be opened and it will remain closed. It will remain closed. So this is a very interesting and elegant example. Uh, it's a very interesting and elegant real-time example. And in this example, one important thing to note here is that there are no final states here. We don't have any final states. We have only two states, Q0 and Q1, which represents closed and open positions. So there are no final states. So when we started off, I said that there can be DFAs without any final states. So this is an example. This is a typical example of a DFA where there are no final states at all. And there is no concept of accepting any particular string patterns here in this example. This is a control system where we want to move, where we want to actually actually provide transitions from one state to another. For example, if you if you are in a closed state, upon getting a QR, you will move to an open state. And if you're at open state and if you move inside, then the flaps will move to a closed position. So we are only looking at the transitions from one state to another, and we don't have a concept of accepting any particular pattern of strings here. That's why we don't have any final states here. Hope this example makes sense and it is clear to you. Now, as an assignment, you can try to design a DFA. I can try to design a DFA for accepting all the binary strings, binary strings, all binary strings ending in 00. So you can do it as an assignment. So you have to design a DFA to uh, accept all the binary strings. Let me write it. We have to design a DFA to accept all the binary strings ending in 00. So in this video, we looked at a number of examples of designing a finite automata. We have actually not looked into the mathematical definition of a DFA. So, but actually we have done some design, we have designed some DFAs based on intuitions. So in the next video, we will be looking at the mathematical definition of a DFA, how a DFA is defined mathematically. And we'll also look at how to draw transition tables. So far we are looking at all the examples that we have drawn is based on transition diagrams. And there is another way of doing this. There's another way of representing a DFA, which is by making use of a transition table. So in the next video, we'll do the mathematical definition of a DFA, as well as we will also look into representing a DFA using a transition table. Okay, thank you.